In last class, we have given some assignments on semicircle and quarter circle. Now, in this class, we will discuss few formulation before we start discussing what will be the moment of inertia of composite section. So, what are the formulas available with? Say, for rectangle, moment of inertia this is the rectangle. The moment of inertia about the centroidal x-axis and centroidal y-axis are this one. Now, why we are interested in formulas? Because in derivation of composite section, we will deal with several geometries, which are the combination of several other geometrical figures. Like you can get a combination of rectangle and triangle, you can get a combination of rectangle and circle. So we need to know the moment of inertia value of each component separately so that we can derive the formulation for the whole body. Okay, so then we developed the moment of inertia of a triangle, say this is the centroidal x-axis, and the moment of inertia of this triangle about the centroidal x-axis was Vh cubed by what is it? It is 36, Vh cubed by 36. Okay. Now similarly, if we do this with respect to y, it will be vice versa. Okay. If we have moment of inertia of a circle, then we did the moment of inertia of a circle about the diametrical axes. So this is the x and y axis, and we got it at, I'm writing in terms of r, so pi r to the power 4 by 4. You can write it in terms of d also. And for a semicircle, if you have calculated the assignment, so you will get the semicircle will be about the centroidal y-axis. It is basically pi r to the power 4 by 8. Okay. And if you do a quadrant circle or a quarter circle, that is basically this figure. If we take this is as y and this is as x, then for both the axes they are similar, and the formulation is 0.055 r to the power 4. So these are the all formulations of a popular figure. Now there are some solids also. For solids, now if we have a sphere, then we must know the center of gravity of this sphere. The center of gravity of this sphere is at a dy2 location, and we know all, if it is a cone, a right circular cone, then it is at a distance h/4 from the base. If it is a hemisphere, then it is 3r/8 from the flat surface. Okay, so now we will deal with composite section and how to calculate. I will explain briefly how to calculate the moment of inertia of a composite section. Say, let me start with a smaller problem, short one, preferably a T section. Okay, so the problem one, we have a T section. It looks like a T. Dimensions are given, say this is 60 millimeter, so this is 10 millimeter, this is also 10 millimeter, and this is say this distance is 90 millimeter. Okay, this distance is 90 millimeter. So we can think of this T as a combination of two separate rectangles. So the first work for us is to determine the axes. So if the figure is symmetrical, always choose your axis like this at center. It reduces your calculation. Now the question is, what is moment of inertia about centroidal axis, centroidal x-axis. So we don't know the centroid yet. We need to find out what is the centroid, and then we will proceed using calculation. So first of all, to find out centroid, we need to make a chart. The chart looks like this one. There is a section 1 and 2. We have two components, section 1, this upper rectangle, and this vertical rectangle as section 2. So for each section we need to calculate their area, their centroidal distance, and multiplication product of these two. So for the first one, say this is our section 1 and this is our section 2. So for section 1, the area is 60 into 10. The unit of area you need to write it millimeter. Now this is our axis and this is origin. This is x-axis, this is y-axis. So the centroid of this rectangle lies here. Only for this one. The location or the distance from this point, from this axis is this y bar. So we are terming it as y bar 1. So this distance is 90 and half of 10. So 90 plus 10 by 2, that is 95. And this was 600. So that area A1 Y1, this product is 600 into 95. Okay, so if you do that, let me do it. It is coming as this much. Please check the calculations. I am doing with the old calculator. Now the next part, the part 2, this section 2. The section 2 is this one. So that area is this is 10 and this distance from here to here is 90. So 90 into 10, that is 900. Okay, and the centroid lies here at the middle of this rectangle. So that is y bar 2, and that is simply 90 by 2, that is 45. So that area A2 y2 is basically 900 into 45. So how much it is coming? It is coming as 40500. That much millimeter cube. Okay. So the chart is complete. Now to find out the centroid, of the whole section, this value, we know the formula is, what is the formula? A1y1 plus A2y2 divided by A1 plus A2. So that is coming as 5700 000 40500, and A1 A2 is 600 plus 900. So if you calculate this, you are getting this as 65 millimeter. Okay, so from the base at this x-axis passing through this base, the distance of centroid is, or the centroidal x-axis lies at a distance 65 millimeters. So the 65 is, this is 45. So 65 should be above this one. So I'm marking this centroidal x-axis. Okay, centroidal x-axis. Now the moment of inertia I of the whole body is basically the summation of moment of inertia of section 1 and section 2. Okay, section 1 and section 2. Now what is the moment of inertia of section 1? Look, we need to calculate moment of inertia of section 1 about this axis, but we know the moment of inertia of section 1 about its own axis. We know it. Okay, there is a rectangle and the moment of inertia about its own axis, say x1 x1, we know it, that is bh cubed by 12. Then we need to use the parallel axis theorem. If we know the moment of inertia about this axis, you can get the moment of inertia about this axis. This is the philosophy. Okay, so this is for I1. I'm writing. It is not visible. Okay, So for I1, let me write it here. Okay. So for I1, the moment of inertia of this is B. This is H cubed by 12. That is about this section, about this axis x1, plus we need to know this distance because we are going to apply parallel axis theorem. So about x1, the moment of inertia is 60 into 10 to the power cube by 12, plus the moment of inertia, if you want to calculate about this axis xc, then it will be its area, that is 16 to 10 into square of the distance between these two axes. Now this axis x1, where it is lies? It is lies at a distance 95 from this axis, and this xc, it is lies at a distance 65. So the distance between these two is 95 minus 65 square. So I'm writing this down here again. So it is B h cubed by 12. This is basically the moment of inertia of section 1 about the axis x1, plus by applying parallel axis theorem, area of the rectangle into square of the distance between the axes. So this is basically your I1. Now similarly we can find I2. Now what is I2? Space is very limited. So for I2 you need to consider only this rectangle. So we know the moment of inertia of this rectangle about this axis, about its own centroidal x-axis, x2. So that is B 10, h cube, that is 19. So B h cube by 12 plus the area of this rectangle. The area is 90 into 10 into square of the distance between these two axes. We know the moment of inertia about this axis. We want to find out the moment of inertia about this axis. So you need to know the distance between these two. So now this distance is from this x-axis is basically the distance of this centroid, which is 45. So this is 45, and this distance from this base to this one, this was as this was 65. This is 65. So 65 minus 45. So 65 minus 45 square. So this is the moment of inertia of section 2 about the centroidal x-axis. So let me rewrite this one. So first of all, this is B h cubed by 12 plus area due to parallel axis theorem, square of the distance between the axes. So this is I1. I1 means the moment of inertia of section 1 about this centroidal x-axis, this axis. Okay, I'm darkening it. We want to find out the whole section, moment of inertia of the whole section about this axis. So we need to find the moment of inertia of section 1 about its own axis, then apply parallel axis theorem. Similarly, find the moment of inertia of this rectangle about its own centroidal axis x2, then apply parallel axis theorem. So if you calculate this, this is just a calculation. So it will come as 151 2500. Okay, and the unit will be millimeter to the power. So this will be the moment of inertia of the composite section about its own centroidal x-axis. In similar way, we can do for y-axis also. So try this problem at home, and if you have difficulty, reply me back and wait for the next figure. In next figure, we will do I section, and it will be continued through some other section till we end this chapter. Okay, thank you.